Hi, this is Professor Fernandez, and we are talking about class notes D in lesson 8 here. So this class notes is about understanding the possible solution categories in the case of a linear system with only two equations and two unknowns. Okay. So this is going to be something like, well, I'll just write the equations first. So this is going to be something like ax plus by equals, let's call it k1. And then dx plus, let's keep going with the alphabet here. How about cx plus dy equals k2? All right, so this is a linear system, two equations, two unknowns, and we're going to understand the theorem above, which talks about the three solution categories. It says that linear systems either have no solution, infinitely many solutions, meaning an infinite number, or a unique solution. Okay, just one solution. All right, so what I wanted to do in this in this class notes is help you understand, get some intuition for why those are the three categories and how this might make sense. And often when you do that in math, you want to look at a low-dimensional example. So certainly a system of two equations and two unknowns is a pretty good place to start. So here's how I'm going to convince you that these are the only three possibilities for the solutions to this system. How am I going to do that? So I'm going to use a little bit of geometry and rely on what you already know about lines. So what do I mean by that? So the first equation here, I'm going to solve for y. Yeah, I'm going to solve for y. I'll do this first and then I'll come back. So if I write this out, I will move to the right-hand side the term ax, and then I will divide by b. So this is k1 over b minus a over bx. Great. And the second equation here, I'm also going to solve for y. So I move over the x term, cx, and then I divide by d. Okay, so I get k2 over d minus c over dx. All right. This assumes, of course, that b and d are non-zero. That's kind of why I hesitated a minute ago, because I thought maybe I should do things in the most generality possible to begin with, but I'm going to instead show you the main punchline, and then we'll come back and generalize a little bit. So the point is that we have now obtained what should be familiar to you. This is the equation of a line. And so is this one. Great. So if I want a solution to this system, right, what am I looking for? I'm looking for an x and y value that satisfies both of these equations. Okay, that's thinking of it in terms of algebra. But now that we've realized that geometrically these equations are just, the graphs of these equations are lines, a solution is going to be a point where the lines intersect. So now basically we have a way to figure this out. So what can happen, right? If I draw two random lines, right? Here are two lines. What can happen? Well, this is the first thing that can happen. The lines can be parallel. So parallel. Okay. This happens if they have the same slope, a over b equals c over d, but they have different y-intercepts. Okay. Then you can see that the lines are never going to intersect. They're never going to intersect. So therefore, there will be no solution. There is no point x comma y that is on both of these lines when they're parallel. Okay, the second thing that can happen is the two lines can intersect just once. Okay, so this is a unique intersection, and that happens effectively when the lines are not parallel. Okay, and not the same line. Okay. In other words, as I've drawn it over here, right, I've drawn two different lines, right? They are not on top of each other. They're two different lines. And I've drawn them such that they're not parallel. So that is going to give me a unique intersection point, right? So in this parlance of linear algebra, we get a unique solution to our original system. Why? Because there is only one point that is on both lines. So there's only one solution to the linear system that the lines represent. And then we go back now to the third case. So the third case is the case where both of these equations are exactly the same line, right? So, an example might be like, oh, I'm solving the linear system x plus y equals 0 and x plus y equals 0, right? It's the same equation, so they represent the exact same line. So whatever x and y values work here are going to be the same ones that work there. There are an infinite number that work, right? So -1 plus 1 is 0. -2 plus 2 is 0. -3 plus 3 is 0. So infinite number of solutions because every single point on this line satisfies the system. So I'm going to write here infinite number of intersection points, okay? If and only if they are the same line, okay? Literally the same line. So in terms of linear algebra, therefore we get infinitely many solutions. Okay. So again, this is meant to convince you that even in this low order, low dimension setting, where if I scroll back a little bit here, I have just two equations and two unknowns. Geometrically, there are only three possibilities for what that represents. It represents either a non-intersection of two lines when they're parallel, a intersection at a unique point in two lines when they're not parallel and they're not the same line, or when they are literally the same line and then obviously they intersect at every single point on any one of those lines. So you have an infinite number of solutions. All right, so that's it for this video.